hēRo3 is a secure cloud platform for building, running, and sharing both Markov cohort and partition survival models. All the calculations are performed by hēRo3, which is a free and open source R package, which is running in a virtual private cloud at AWS. And I'm going to put emphasis on this component of it because it's why it's such a powerful tool for doing model validation. Next, please. So as I alluded to earlier, we know that hēRo3 is being used for rapid development of early economic models. Model prototyping is another area where use is exploding. But we're going to be focusing on the third element of use, which is the validation of models, typically models in Excel. And as I noted, because its calculations are based on heavily tested open source R package, and since most Excel models can be replicated in hēRo3 literally in hours, it's an ideal tool for validating either legacy or new models in Excel. And what we're going to show you today is not only the rapid replication, but also how that replicate model can be used to quickly find calculation errors in models in Excel, or alternatively, if you happen to get lucky, establish that the model that you're working with in Excel is error-free. And I cannot overemphasize the importance of this, especially when you're using models in Excel for HTA submissions. To get it wrong, to submit a model with errors can have potentially huge consequences. Next, please. And the problem is that, visual inspection of models in Excel is literally impossible to do because most models that you're working with, they have tens of thousands, hundreds of thousands, sometimes even millions of cells. And you literally can't inspect them for errors manually or visually. So we're going to be talking today about how to use hēRo3's export to Excel functionality, along with a tool that I think we've discussed with some of you in the past, or many of you in the past, which is a flowchart. And it's a tool precisely to aid you in validating models using hēRo3, export to Excel functionality. You create a replicate in hēRo3, use export to Excel, and then how you can utilize that functionality and the flowchart to very quickly identify errors in models, or alternatively confirm that they're being done correctly. So we decided to take what is I think, an interesting case study. Many of you perhaps cut your teeth as modelers at HEOR professionals on the Briggs, Sculfer, and Claxton textbook. It's a classic and probably the most widely used textbook to teach modeling. And the second case study that they have there is called Exercise 3.5. Next, please. Which is a model that compares the cost effectiveness of a new prosthesis for total hip replacement to a standard prosthetic device. It's a four-state Markov cohort model, not terribly complex. The states being successful primary procedure, a revision total hip replacement, successful revision, and death. And this is the second model or exercise in their text. And it's the one that they use to introduce the concept of time-dependent transition probabilities. Next, please. And this is the schematic that Briggs et al. Have in their textbook, and you can see the model. It's a fairly straightforward Markov cohort model. Next, please. So the problem that we have is that Briggs et al., and it's maybe difficult for some of you to see the numbers that are circled, we went about creating our own version of this model, and you can see the numbers that we obtained, the outcomes and the costs over on the right, as well as the cost per quality. But Briggs et al. Report out their outcomes and costs for their model with those numbers on the left that are circled. So we have a problem here. We created a model. It is not yielding the correct outcome, the correct results, and we'd like to understand why. Now, next, please. In reality, that's not the situation that we face, right? We don't have a gold standard model for every model in Excel and against which you can compare the version of the model in Excel that you're working with. In actual practice, the situation we face is that we don't know what the true state of affairs is, which is the big question mark on the left, and we simply have a model, which is in Excel, which is represented on the right, that is yielding output, and we don't know whether or not it's correct. And I would argue that the field research that's been done suggests that probably somewhere between 70 to 80% of all models in Excel contain errors. So our priors with any model in Excel should be that, in fact, they do contain errors, and the challenge will be how do you validate it before you make use of it, be it either a legacy model or a new model that might have been developed as part and parcel of for an HTA submission. So what I'm going to do at this point in time, we're fortunate because the exercise 3.5, if you look in the templates model, templates section of your hēRo3 workspace, you'll see that we have a couple of the Briggs models set up in hēRo3. So Rebecca is going to walk us through the setup of this total hip replacement model, and then Jordan is going to do the lifting from there and show us how we can use the replicate in hēRo3 to chase down the errors in our model in Excel, which in this instance we know has errors in it because it's not yielding the same results as Andy and his colleagues report. Rebecca?
Thanks, Jay. So I'm just going to switch back to hēRo3 as usual. I'm going to just zoom in slightly and go full screen. So here is the Briggs exercise 3.5 webinar model. I do want to note to anyone who might be following along in the templates or look at the templates later, we've adjusted this model ever so slightly on the values page now that we have the ability to apply values at model start. And we have not yet updated the model in the template section, and I'll call that out when we go to the value section. So here on the settings, everything in this model is based on both the Briggs exercise in the textbook as well as their template Excel workbook. So that is a template that is provided with online to go with the textbook that calls out specific parameters and provides them with some starting off tables. So a few things that we do know is that this is going to be a UK model, that our discounts for outcomes and costs are actually going to differ, with costs being discounted at 6%. We have a cycle length of 1 year with a 60-year time frame. And the difference is that we are using the START method of half cycle correction. So again, that is assuming that patients transition at the start of a cycle and state membership calculated based on the end of the cycle. And one reason we're doing that is because of that initial hip replacement. We're not holding them in that state. We're going to look at what happens right after the hip replacement. So as we go forward, we don't have any groups in this model. For those of you who are familiar with this exercise, it does look at men and women, but it never looks at them combined. So we haven't used the group functionality to do that. We've used a drop-down instead. As Jerry mentioned and pointed out, our health states in this model are going to be the primary total hip replacement, which is where all patients enter. It's going to be an apologies, let me make this full so we can see that. So it's going to be a successful primary first hip replacement. Then there is a revision hip replacement, and finally a successful revision. And obviously the probability of death. As we know, our strategies are going to be just that standard hip replacement and the new prosthesis. And then for our transitions, I've actually already gone ahead and grouped them by the from state. As usual, I'm going to pause here and just move over to the parameters so we can take a look at the variables that we have in this model. So in the parameters, I've also already gone ahead and view group by row by categories. And we just have a few input values, again, taken from the exercise and the template workbook. So this model can either be run for men or women, which we'll see in base case, and it requires a start age. The version of the Excel model we were looking at was based on a start age of 60 years. We also have a regression, a viable regression model that was fit to the probability of needing to undergo a revision. And this regression is based on actually, understandably, a constant value. There's an age coefficient, a coefficient for sex, and then a survival coefficient as well. And all these numbers were provided based on analyses already undertaken. We then have an efficacy input for that new revision. These were estimated on the log normal scale, or excuse me, the log scale, and that's why they need to take the exponential of them. Lastly, we have some additional probabilities. We have probabilities of case fatality following either the primary or the revision hip replacement. And then a probability of undergoing a repeat revision. So after the first revision, what's the probability of undergoing another revision? We have a few cost inputs. So we have the cost of that routine care after a total hip replacement. Since that's the same in both models, it's simply set to 0, excuse me, not models, strategies. We have a cost of a revision hip replacement, and then the initial cost of the standard prosthesis or the new prosthesis. So we'll note that the new prosthesis is more expensive. We have health state utility values for that okay first hip replacement, okay revision, and while persons are undergoing a revision. Lastly, we have a few calculated values. We just have a gender flag. So this will return 1 for men and 0 for women to work with that regression parameter that we have. And finally, we have current age. For parameter calculations, we're just calculating the lambda based on the start age and gender flag and the other items that we have for that regression. And finally, for probabilities, let's just make the formula column fit. Nope, that didn't work. There we go. And if we scroll on over a little bit, we first have general population mortality, which is looking up in a table called life table based on current age. It's pulling from a column based on either if we're running for men and women, and I'll show you this table momentarily. And it's looking for bin equal true, which means not an exact match. Finally, we are just calculating the annual probabilities of needing to undergo revision for either the standard or the new prosthesis, simply based on that regression analysis. So in the tables, that table that we're looking up, general population mortality, is simply a life table with age bands and the annual probability of death for both men and women. So since we're using age bands versus individual annual years, that's why we want to use the bin equals true. So if there's ever age, say 77, it pulls the value that's in the 75 row until the current age meets 85. Returning back to our model then, simply in transition probabilities, again, all patients enter in the primary hip replacement health state. They then either have a probability of death just based on undergoing the hip replacement, or they can remain in state. Apologies. Or they can have finished their first hip replacement and go to OK first. Once in OK first, they can either remain there, that means their hip replacement is fine, die based on general population mortality, or transition to undergo a revision, which is strategy specific. So there will be a slightly lower probability for those who underwent that new, or excuse me, went under a hip replacement and received the new prosthesis of requiring a revision. So once patients do undergo a revision, they move to this revision total hip replacement, which is set up similarly to the primary total hip replacement. They can either die based on general population mortality or the case fatality associated with a revision. And if they survive the procedure, they will then go on to OK revision. Of course, within OK revision, there's still that probability of general population mortality. There's that, we're using that complement C to see if they'll remain in the OK revision state. And then there's that probability of repeat revision again. So that probability will be the same for all strategies. And lastly, just to complete everything, the probability of those who are dead remaining dead will be 1. Now, on the values, what I did want to point out, we're going to go ahead and view row groupings by name, just to collapse some of them. Life years are all very straightforward. For all 3 health states, we're simply looking at cycle length years for the residents within those health states. Qualities are similarly the same for both strategies in this model. So they're just looking at the life years times the health state utilities. There we go. Times the health state utilities for those health states. So we have the utility for OK first for OK first qualities, utility for revision for the revision, and finally the utility for the OK revision. When we move to costs, we're going to have first that cost of the primary THR. And this is the part of the model that I'm mentioning that is set up slightly differently than the model that's currently in the templates. And that's because we now have, as I believe most of you would be aware, the ability to apply values not only based on residence in state or transitions through state, but at model start. So when model start is selected as the value type, the cost or disutility or whichever value you're calculating will be applied to all patients and will not be discounted. So here, all standard patients are going to receive that cost of a standard hip replacement, and it will not be discounted. Same goes for those who receive the new prosthesis. Finally, we simply have the cost of a successful hip replacement. So for both the OK first THR and OK revision THR, simply getting the cost of an OK total hip replacement, which is an annual cost. And finally, the cost of the revision, which is applied for that cycle that they are in the revision health state. As you all know, we would then need to go to summaries and collect our values so that they will accrue as we want. So for life years, we have the 3 life year items, qualities, the 3 qualities, and costs, the 3 cost items. Again, as Jerry was noting, the time dependency in this model is 2-part. One is that general population mortality, which is going to be based on age and current age. And the other is that regression for, for the revision, which is also going to be based on model time. So that's where the time dependency is coming into this model in 2 places. So if we go to the results, and I'm just going to skip over to the incremental CE, we're looking right now at qualities total costs. We see that we are reporting out total qualities approximately 12.57 for the standard prosthesis versus 12.64 for the new prosthesis. Total costs are slightly higher for the new prosthesis, resulting in an ICER of 415. If we go back to the results that our Excel model are reporting, we'll see that our Excel version is reporting out lower qualies, and there's definitely a larger difference between the two sets of qualies, and the costs are much higher, let alone the cost of that new prosthesis. Total cost ends up being lower than the standard. So in the end, in our Excel model currently, the new prosthesis dominates the standard prosthesis. It has higher qualities and costs less. But our hēRo3 model is saying instead it is a cost of £450 per quality gained. So there's some sort of discrepancy. So what we would do, 2 steps, and then we'll hand off to Jordan. We're going to export our model to Excel. Simply by clicking Export to Excel, you can see our model is calculating. Apologies that my bar is in the way. It's now downloaded. We can simply click on it as it opens, and we will have our export. The other thing I just want to quickly touch on, for those of you who may be unaware, to access the flowchart that Jordan's going to be looking at today, you would go to Support Options, up top, this question mark, to the User Guide. And yes, you can use the links in the slides. Apologies, I'm zoomed in still here. But using the User Guide will allow you to always have the most up-to-date either cheat sheet or flowchart. So we're going to training materials. I find it the fastest by just clicking cheat. And once we go to training materials, there we go. We would want to look at the model validation flowchart. We can simply click here and the PDF will open. Jordan, would you like to walk us through the errors at this point then and trying to track down why our results are different?
Yeah, thank you, Rebecca. All right, so I'm going to share my screen now. My screen should be visible. Okay.
It is.
Great. So we're in the very start of the model validation flowchart, and so we'll go through this. And so the first step, now that we've identified that there is a discrepancy, is to check the discounted total costs and outcomes that they're the same. Actually, this is the step that we've already done. We've already checked that the discounted total costs and total outcomes are not matching, right? So we do that check. We check to see if they're the same. Obviously, if they match, there would be nothing to do here. That would be great, but sadly, they don't match, and so we need to move on to the next part of the flowchart, which is right here. And so after we've checked the discounted results, the next step would be to check the undiscounted results. The reason for this is if the undiscounted results match and it's only the discounted results that don't, then we know it's a problem in discounting. And so that's what we can do right now. And so with that, I am going to go over here to the Briggs model in Excel. And here we have the results were reported out separated by undiscounted and discounted. We already know that the discounted don't match. And so now we're going to see, okay, let's take a look at the undiscounted values. And so for cost, it should be about £8,200 for standard, about $7,400 for NP1. And so we'll take a look at that in hēRo3. And we're getting something entirely different here. Actually, let me just turn this on to undiscounted. So here we should be getting more like 887 for standard and then 712 for the new therapy. And so these results clearly don't match, right? These figures are just entirely different. And so that clearly indicates that we are still not matching on the undiscounted results. We can actually continue to look at the life years and qualities, but I think at this point we've identified that this is not purely a discounting issue. So moving on, the next thing is to check all of our line items and cost outcomes and cost line items to see if the discrepancies are isolated in a single item. So for example, is it all in the cost of hip replacement itself, or is it all in qualities in a particular state? If we can identify that all the discrepancies are in a single spot, then we know exactly where to look. Whereas if we can't, if it seems like the errors are more general, then we have a lot more to check through. Now, as it happens, we already know that this is not going to be the case because we've already identified that the qualities and costs are both discrepant. But just to, again, sort of cover this, we can look at the undiscounted life years, and we'll see that those are also off. So in this case, the undiscounted life years are 17.2 and 17.29 in the Excel version. And if we go over to hēRo3 and look at the undiscounted life years, we'll see that 17.58 and 17.59. And so, clearly there is a much more general problem in this Excel model than just the tabulation of one particular line item. This is something that's affecting cost, it's affecting life years, it's affecting qualities, potentially it's affecting multiple line items within each of those. And so this is the kind of broad problem that might be resulting from the transition probabilities being incorrect, and therefore patients being in the wrong states at specific cycles. And so with that, we can continue the flowchart. And so we've established that this discrepancy is not related to a single line item. And so because we're going down this note, the point to start looking at the export to Excel, right? This is the point where we would open up that workbook and start going through that. And so the first thing that we're going to do is go through the trace and compare those across the hēRo3 Excel output versus the Excel model, and check to see that those are identical, or whether or not they're identical. And so we can do that. Now, importantly, normally it would tell you to check the model results with half cycle correction in the Excel model versus that in hēRo3. But as we're going to see in the Briggs model, in the Excel version of the Briggs model, it doesn't really separate out with or without half cycle correction. However, it essentially doesn't apply a half cycle correction, or it implies only an implicit half cycle correction, which amounts to non a half cycle correction. And so we don't have to worry about that distinction in this particular case. So anyway, let's start by identifying where the trace is in our Excel version of the Briggs model. And so that's going to be on these two sheets here, standard and NP1. And I'm just going to zoom in a little bit. So this standard sheet, of course, is through the calculations for the standard therapy. And the trace happens to be these 5 columns right here. And the values are multiplied by 1,000 here, but that's not going to make it too difficult to compare. So anyway, these are the values that we're going to be looking at for standard, and we're going to want to identify the equivalent values in the Excel output from our hēRo3 model so that we can compare them. So moving on to the Excel output from hēRo3. Actually, I have not downloaded that yet, or I have, but I haven't opened it yet. So I will open it now. Okay, and we are going to go to the results trace page right here. So I'm going to the results trace corrected page, but again, it's not going to matter too much in this case because this model doesn't really imply, it doesn't really implement a half cycle correction. So anyway, what we're going to want to do in this page is make sure that we're looking at the standard strategy. So we're just going to filter on that. So you can see the strategy here is standard. And then we're going to look at our 5 health states here. And again, the results on the other model were multiplied by 1,000, but that's not going to make it too hard to compare. And so we'll just start going through this. And so we can look at the first cycle. Of course, everybody starts in primary total hip replacements. And if we go to the Excel model, let me just organize these tabs a little bit better. Everyone starts in primary THR in both versions of the model. And then if we look at the second cycle, we would see that 980 are in success in the Excel version of the model. Whereas in the hēRo3 version of the model, that's also true. 98% are here, and then 2% are in dead. Now, really, if we want to do this efficiently, what we would do is we would copy these values over into our Excel workbook. I need to paste his values. And then we can take those values and divide them by 1,000. Okay. And I'm not going to do them all here just to simplify, keep things going fast here. And then we can just check to see whether the values are different, or alternately how much they differ. And then we can just drag that formula here. And actually, because it's a table, it's not quite working properly. So let me just make sure I get the appropriate F2. Okay, and so we're just going to drag that formula down. So what I'm doing here is I'm calculating the difference between the two cells, the cells here and then the cells here, right? The hēRo3 trace versus the Excel trace that we've pasted in and then divided by 1,000 to put them on the same scale. And what we're starting to see is that starting with the third cycle, there are substantial differences in the trace root calculations. And so at this point, we've identified that there is a problem in the trace calculations. In other words, we're calculating different state membership over time between these two models, starting with the third cycle. And so that's telling us something about what the source of the problem is. It's going to have to be either relating to initial state probabilities or the transition matrix, since those are the two things that impact state membership. And so going back to our flowchart, we've established that the results are not identical for our trace. And so now we can follow this next sort of item in the flowchart, and it'll take us to a different page, which will allow us to check our trace calculations. Okay, so you can see we've jumped to a new page on the flowchart, and now we're going to start checking the trace calculations. The next step would be to check the trace without half-cycle correction. As I've mentioned, this model effectively does not employ a half-cycle correction, or there's no real point to sort of separate this step here. If you had a model which, for example, used the life table method and then reported the results separately with and without that correction, then this would be important to do. However, in this case, we can skip it. So the next question would be, is this a three-state PSM, a three-state partition survival model? The reason this is important, of course, is because if it were a partition survival model, then we'd be dealing with distributions of PFS and OS to check instead of transition matrices, but it's not. And so at that point, we are going to go over here. And so the next thing it wants us to check is to check the first cycle for the trace and to compare that between hēRo3 and Excel. The reason it wants us to check the first cycle specifically is because, as I mentioned previously, there are really only two things that impact state membership in a Markov model: your initial state probabilities and your transition matrices. And it's possible that the error could be limited just to the initial state probabilities, and in fact, our transition matrices are exactly right, and it's just we start patients in the wrong state. However, as we've already seen, the first cycle, we are getting the right answer of everybody starts in primary total hip replacement in both models, as we can see here. And so clearly that's not the issue. The issue is not the initial state probabilities. And so we can say that clearly that the first cycle results do not match, and therefore the first cycle results do match, and therefore we have to go down here to the next step of our check. So again, there were two possible explanations for the discrepancy in the traces. One was that the initial state probabilities were wrong. The others was that the transition matrices are wrong. In principle, they could both be wrong, but we want to rule out the fact that it's the initial state probabilities, and we've ruled that out. And so now we're going to start checking the transition probabilities to see what the problem is there. And so we're going to move on down here. So first we got to check the formulas on the transitions page, and to just check to see that those are doing the same thing as the formulas in the Excel model. Now, this is going to be a slightly tricky comparison because the Briggs model is set up really without a proper transition matrix laid out. It just sort of implicitly does that in the trace calculations. And so we're just going to have to spend a little bit of time looking to see what we need to compare. And so starting with our hēRo3 model, let me find that. Starting with our hēRo3 model, we're going to go to the transitions page. And we're going to just sort of note here what these sort of transitions being referenced are. And so, and really, the important thing to note here in our hēRo3 transitions page is that there's actually virtually no calculations going on. And so thankfully, this is going to be a fairly simple process. For the sake of time, we're going to skip over bits of it. But ultimately, what we want to make sure here is that we're plugging in the appropriate formula for each one of these rows in our transitions page. And so in this case, we're just looking at primary THR to dead, and it's referencing this variable case fatality first THR. And that's right, that's the variable it should be referencing. Now, whether that variable is doing what it should be doing, that's something that we'll get to later, but this is the appropriate thing to reference. Similarly, this is going from primary THR to OK first THR. This is the appropriate formula. And as we go down the list, I'll sort of save sort of the detail here, but these are all the appropriate formulas that we should be having, right? If we actually spent, the 10 minutes or so necessary to check each one of these to make sure that the formula here was entered properly, we would see that this is correct, and it's referencing the same things that the Excel model is in fact referencing. And then, of course, the equivalent of that in our Excel model would be in the standard page, or in P1 if we wanted to look at that strategy, would be buried within the trace calculations. We could see, the transition probabilities are really embedded inside here. So for example, if we look at this formula right here, this is the probability of being in primary THR in the previous cycle times 1 minus this variable. And so this 1 minus this variable is the probability of going from primary THR to success primary. And so again, we don't have the time to go over every single item in there, but suffice it to say that if we went through those checks, we would find that the formulas in our hēRo3 model are doing exactly the same thing as the formulas in this Excel model. They're referencing the same variable. But that doesn't actually show that our transition matrices are correct. It's one thing to reference the correct variable, but then we have to start tracing back the calculations in those variables to make sure that the the variables themselves are calculated properly. And ultimately, if we trace those back, we should find a problem, because we know that the initial probabilities are correct. We know that our transition matrices are incorrect, and therefore, and we know that the formulas on the transitions page are correct, and that these are the formulas in this Excel workbook here are correct. And so we just need to sort of continue tracing it back until we find that those are referencing something that's incorrect. And so as we do that, we would start sort of going back and taking a look at all the different variables that this Excel model is referencing, like this OMR PTHR and the standard RR and so on. Everything that we find that these cells are referencing, we would start tracing back. And similarly, in our hēRo3 model, we would be looking at these formulas and tracing them back. And then ultimately, we would find some point at which they're discrepant, and then we would resolve that discrepancy, and then hopefully that would have fixed the model. And so we'll start doing that. So we'll go to the variables page over here and start looking at some of the variables that were being referenced. And as we look through the variables, actually, many of them are pretty trivial. They're just inputs, right? And so in this case, we could just check to see that these inputs are the same. But as we go through this, one of the ones that we'd be looking at is this RFS lambda variable, right? Rebecca actually called this out previously, that this is basically a a regression equation. And let me just make this a little bit more legible by separating out the operators here. This is essentially a a linear predictor from our model that predicts this revision-free survival. And so the way this is set up in the hēRo3 model, of course, is you've got a constant, and then you've got some coefficient multiplied by one of these variables, and then another coefficient multiplied by the gender, and so on. And so this is generating our linear predictor, which is then exponentiated to generate the appropriate value of that lambda. Now we can find the same variable, and this is again something that's referenced in our transition matrix. Now, if we look and find the same variable in Excel, and this is again one of the ones that we'd be tracing back, we can look at the exact same thing here, and that would be in this parameters page. So as we trace this back, we would see, okay, what does that look like? And so in Excel, we're again exponentiating, and we've got the sort of age covariate times the age coefficient, and the male coefficient times the male covariate. But actually, it turns out that we're missing the constant here. So this appears to be an error, right? If we are setting up this regression equation properly that then feeds into our transition matrices, then of course we're going to get the wrong transition probabilities and therefore an incorrect trace. And so we can just actually fix this by putting in the appropriate value there. And so at that point, hopefully we fixed our problem. And so we can actually just take a look now and see if our overall sort of results match here. And so our outcomes now for hēRo3, they're unchanged because there was no problem identified in the hēRo3 model. So it's 17.58 undiscounted life years and 17.59 undiscounted life years for the other strategy. And then over here, over here, we are actually now matching on the life years. So that's great. We've made an improvement here. Moving on. Oops, I just accidentally left out of that. Let me go back into there and go back to where we were. And so I guess the real question now, though, is do the traces match? And we know that they do because they're producing the same life years. However, what we're going to find here is that the qualies are not going to match the undiscounted qualies. So if we check the undiscounted qualies, we'll see that it's 14.57 for standard and 14.93 for the new drug. And if we go to hēRo3 and we look at the undiscounted qualies, what we get is 14.83 and 14.93. And so the new strategy is matching at 14.93, but for standard, it's not. It's at 14.57 instead of 14.83. And so at this point, we still have a problem. We've fixed the trace. And we know this because the life years, the undiscounted life years match. But there's still some problem in the calculation of qualies. And so we have to keep going through the flowchart to identify that problem. And so this is where we were. Again, we were checking the trace. We fixed the problem. We've now found that they do match, but we need to continue to checking outcomes and costs to find the remaining error or errors in our model. So the step here would be to check the discounted total costs and outcomes to match the, oops, this is taking me to, is the right spot. Apologies, this was the wrong link here. So we will fix that in the workbook. Where it should be taking me is to the check the values calculation. And so in the first step of this checking the values calculation, which we're again doing to track down this problem that's now isolated to qualies, we're going to go to the unit values sheet of our Excel export. And that is right here. And so what this sheet is doing is it's telling us essentially what the formulas on the values page are calculating to. And more specifically, what that means is the amount of a particular line item that will accrue in a particular state if the patient is in that state in that particular cycle. Typically, if you're looking at qualies, that would mean that the result of this unit values calculation is going to be the number of qualies that accrue in a cycle. And we're going to filter on standard therapy here because we know that the problem is isolated there. And we're also going to focus on the qualies because we know that the problem is isolated there. we don't have to look at the dead state here because that's not going to be very interesting. And also because our utility values are not time dependent in this model, we can just look at the first cycle, and this will enable us to just sort of more quickly identify what's going on. I'm also going to freeze my panes here just to make it easier to scroll. And so what we're going to see here is what the utility values are that we're using in each state. It happens to be utility values because these are annual cycles. It wouldn't be utility values if we had cycle lengths that were less or greater than annual, because it's actually not the utility value per se, it's the number accrued. But anyway, in this case, we can interpret them as utility values because the cycle length is 1 year. And so what we're seeing is that there's a utility value of 0.85 for first THR. What we're seeing is a utility value of 0.75 for revision. We're seeing a utility value of, so this is OK revision. So then we're seeing a utility value 0.3 for revision. And then for primary THR, we're seeing a utility value of, where is primary THR? Rebecca, correct me if I'm wrong. Do we not count that first cycle, that first date? Do we not calculate a utility value for that one?
No, it doesn't have a utility value because it's using the start method. So they're never actually residing in that other state.
Great. OK, so there's the answer there. So the answer is that the utility value in that state is irrelevant. So anyway, so those are the utility values that we're seeing. 0.85 in first THR, 0.75 in OK revision, and 0.3 in revision THR. And so now let's check that against what's being used in the Excel version of the model, specifically for standard. And so in our Koalis calculation, right here, you can see that there's this calculation here where it's U success times H7, which is the success date. And so we'll track down what U success is, make sure that's the appropriate value. U revision times standard, times sort of revision THR right here. And then U revision times the success. So actually, just right off the bat, there's a little problem here, right? So using success for this state makes sense. Using revision for the revision state makes sense. But using the utility value for revision for the success on revision, that would be wrong. These two states are supposed to have different utility values. And so that could be the cause of our problem, right? We've identified sort of the equivalent sort of calculations here in Excel, where it's using the wrong utility value. And so we can actually fix that. And so I think the utility value here is U success R. And so we can fix that, and then we can update those calculations. And so at this point, we can actually look at what the appropriate sort of values are that we've sort of calculated for qualies. And what we see here is that we're now getting 14.83 for standard. And if we go over to our hēRo3 model, we're also getting 14.83. So we've actually gone through here and we've now eliminated the last sort of discrepancy in our qualies and our life years. We can actually also double check the undiscounted costs and make sure that those are good now. And so what we're getting is 887 here and 712 here for our undiscounted total costs. And over here, 887, it's actually 888, but if we round, then it's 887. And then 713, it would be 712 if we rounded. So these are actually all correct. So we've matched on all of our undiscounted results. But we do need to go back to the beginning now because we've established that the undiscounted results are correct, but now we need to go back and establish that the discounted results are correct. So we just go back to the beginning of our flowchart where we're checking the discounted results. And we can see here that our discounted cost should be 607 and 636. And going back to hēRo3, we can look at the discounted ones. So 607 and 636. And so those match. Similarly, we can look at outcomes. We can look at our discounted qualies. And so here we have 12.57 and 12.64. And here we have much less than that. So here it's 8.21 and 8.34. So there's still a problem here. We still are not matching on our qualities. Similarly, if we look at our discounted life years, we'll see 14.88 and 14.89. And over here, it's 9.82 and 9.82. So we've got a problem. We've got another problem in the discounting. And so going through the flowchart, we can see that the discounted don't match. The undiscounted do match because we fixed those. And so now we're going to the discounting calculations. And so we're going to go through there. So first thing we're going to do is we're going to check the discounting method to make sure that the discounting method is the same. And so specifically, this relates to what time during the cycle that discounting is applied. Do you go based on the start time of the cycle or the end time of the cycle? We're a little bit short in time, but just to sort of skip ahead here, it turns out the discounting method that's used here is the same. So the next step would be to check to see if the Excel model uses something unsupported relating to discounting. When I say unsupported, something that hēRo3 doesn't support, meaning specifically like time varying rates. And it turns out that there is, it's not doing that, right? We're not using time varying rates in this Excel model. That would be pretty easy to check, but in this case, it is a constant discounted rate. And so next up would be to check in any errors in discounting in the Excel model, because if we're using the right methods and the same methods between the hēRo3 model and the Excel model, then the results should come out the same. And if they don't come out the same, there's some type of error. And so we're just going to check that. So first off, we'll go to the standard page and check how discounting is being applied. Now, unfortunately, this model doesn't actually show you the discount rates being used cycle by cycle anywhere. It's sort of embedded in the calculations. A really good best practice is to show the discount factor cycle by cycle so that someone can easily verify that. But to check it here, what we're going to do is we're going to look at the discounted calculations and sort of see what's being referenced. So first off, let's look at the cost calculation. So the cost calculations for the first cycle, you'll note that there's no discounting here. This is sort of an ad hoc way of doing discounting. Normally, you wouldn't use a different formula for the first cycle as the second cycle. But in this case, the first cycle doesn't need to be discounted because it's at time 0, and so no discount is applied. And so that's fine. We go to the second cycle, and we see that the formula changes. Again, not a best practice here, but we're working with the Excel model we have, not the Excel model we want. And what we're seeing is the discounting factor is being applied right here. And so it's 1 plus this cost discount rate and then being raised to the power of the current cycle. And so that's fine. And as we look at other cycles, this is all being calculated properly. We don't need to worry about our discounting for cost. Looking at the discounting for life years, we can do sort of the same thing. So you can see that there is no outcomes calculation for the first cycle, but there is for the second cycle, and that's fine. And here we're doing the same formula for calculating the discounting, 1 to the cost discount rate. Oh, wait, cost discount rate. Okay, so this is a problem. Our Excel model and our hēRo3 model both have different discount rates for costs and outcomes. And it appears here that we're applying the cost discount rate to an outcome. And so that would be an error. And so we can fix that for life years, as we've done there. We should check to see that the qualities to see if it does it. And in fact, it also has that error. And so we'll fix that here. And fix that there. We should also check the other strategy to make sure that it's not making the same mistake. And so we can look at the discounted life years here, and it is making the same mistake. And it's making the same mistake for qualities as well. So we have to fix those. And so it turns out basically all of the discounting for our outcomes was using the cost discount rate instead of the outcomes discount rate. And now that we fixed that, we can check to see what our new outcomes are. So here we're getting 12.37 discounted qualities and 12.64 discounted quality. 12.37 for standard and 12.64 for the new drug. And if we switch this over to qualities, This is 12.57, 12.64. So it looks like there was still one error remaining, but we're running a bit short on time here. I think this is probably a good spot to stop and open up the floor to questions.